Hello, everyone. This is Ted Wertheimer, and I'm happy to present a little bit of information regarding high performance with MSC Nastran. And before we really get started, I really want to, say what some of the objectives are. Really, what high performance computing is for is to allow you, the user, to be able to solve larger models to achieve greater accuracy, and of course, to also give you an opportunity to try more design studies in the same amount of wall time, and of course, to make sure that we can get our products to market in a timely manner and in a high reliability, high quality manner. So what we're going to talk about a little bit is we're going to talk about trends. There really is a large amount of material that we could talk about. We could easily talk a whole day on these subjects. We'll talk about solver technology, which is the heart of solving a set of linear equations, both direct methods and iterative methods, eigenvalue extraction, memory and I/O enhancements that have occurred recently. Then we'll branch over and talk about GPU computing and what that can do to accelerate performance. Then we'll go back to some applications in terms of acoustics, optimization, and aeroelasticity, and dynamic explicit analysis. So effectively, MSC Nastran has really been a leader in terms of solving very large models, both for linear static systems, SOL101, for nonlinear systems now with SOL400 in an implicit manner. And of course, the solution of the linear equations is important for many solution sequences within MSC Nastran. So over the period of time, we've continued working to evolve the parallel processing capability, both using distributed memory computing and using shared memory parallel computing. So what you can see is effectively using a combination of distributed memory processing between 1, 2, and 4 domains, or even a greater number of domains, and in conjunction with that, using shared memory processing, we can see a continuous reduction in the total time to perform a simulation. And what we're doing always in this process is we're really looking at total times. We're not just looking at the solver time. So that includes things like the input and the output, which is difficult to parallelize. We also have iterative solvers, and in recent years we've done more work with that. MSC Nastran has 2 iterative solvers. And one of the areas of improvement has really been in the implementation of this iterative solver to reduce the amount of communication time. And what that does for us is, comparing this versus some other solver, basically we have, even in a serial manner, we have faster performance, or we did even a while back. And even when comparing these things in a parallel manner, we can basically get, with serial analysis, effectively sometimes the same performance that other folks require parallel processing to do. Iterative solvers are one of the things that we think that a lot of users could take advantage even more in problems that are well conditioned, like in problems of heat transfer analysis, or in problems such as powertrain simulation. So this was an example of a heat transfer problem that was performed using the iterative solver. And these are basically the CPU times using a direct solver and using an iterative solver, or the wall times. And you can see that using smarter algorithms can do a tremendous amount in reducing your wall time. Well, eigenvalue analysis is a critical part of MSC Nastran. It's the heart of NVH, noise, vibration, and hardness analysis. It's the backbone one of acoustic simulation. And the procedure that's used in MSC Nastran is ACMS. ACMS stands for Automated Component Mode Synthesis. What we effectively do is we take your model and we divide it up into domains, and then those domains are utilized across multiple machines in either a distributed memory architecture or in a shared memory architecture or a combination of the two. And so we've had an evolution of the process of improving the computational speed. Of course, during the same period of time, there's been an evolution by you, our users, and society of basically increasing the number of degrees of freedom in the model and increasing the number of modes in the model. So the increase in the number of degrees of freedom is generally speaking driven by accuracy and the need to capture fine features, and the requirement that we want to use the same numerical model for NVH, for durability, and for crash. The requirement of dealing with more modes or more frequencies is because effectively we want to be able to capture the higher frequencies of the response to get better ride or better simulation in our analysis. So effectively we can see here, and this is a kind of a typical model that's run today, about 7.3 million degrees of freedom, and effectively through the years, and this is really continuing in the 2012 release and the upcoming 2013 release, utilizing the same hardware but using smarter algorithms and better utilization of parallelization, our effective wall time reduces. We did a whole sequence of these types of problems, and effectively, depending on the model size, people always say, how fast can you scale? How much do you scale? These things are very, very much problem dependent, and that will be repeated over and over during the next 45 minutes. So in cases that are very compute intensive, we generally have effectively much better improvement year over year, and in terms of utilizing greater parallelization in the simulation. But when we do NVH, life is more than just doing eigenvalues. Life also is basically the frequency response calculations. Life is also a matter of basically writing out the output, whether or not it's an OP2 or an XDB. And effectively, we have a balanced approach. So we not only focus on eigenvalue analysis, we focus on what we consider fast FR as well. So this was a typical, again, model in the 8 million degrees of freedom range, lots of modes, lots of forcing functions, and we can see that effectively in the later releases, the current release of the product, we're effectively 12 times faster than what we were just a few years ago. And we are continuing to work to improve these algorithms. So not only doing traditional real eigenvalue analysis of symmetric systems, but also problems that lead to complex eigenvalue analysis, such as rotor dynamics, such as perhaps problems that have damping or problems that involve friction. We also have improved the numerical techniques to solve these problems as well. And this brings us to kind of the change that has occurred from moving to 4 to 6 million types of degrees of freedom models, now to 20 million degrees of freedom models, such as this particular automobile supplier. And looking at the number of modes that are being extracted, we see that we're going up to higher frequencies. We're extracting more modes in the system. We're basically doing our frequency range in more steps of smaller changes in the mode number, and we're effectively seeing that in such models that we can see between doing it on a 4-domain system or a 16-domain system, really 8 domains in the core part of the analysis, we can have a reduction of time by a factor of 2. So for many of these are quite incredibly large models, but it really is only getting bigger. And so this is another model that's been done recently. This is 94 million degrees of freedom. Here, what we're basically seeing is the element size is becoming very small. It's about 1.5 millimeter type element size. And again, we can perform eigenvalue analysis in these models. Again, when you're talking about jobs that are 94 million degrees of freedom, you need really a total solution. That means not only do you need to have the correct software from MSC, you also need to have the correct hardware, you need to have the right amount of memory, you need to have the right disk system, because effectively the amount of I/O just on post-processing, a problem with 94 million degrees of freedom, is a challenging problem. But this problem that's a challenging problem today will probably become routine tomorrow. So in terms of memory, really all of MCAE has evolved since when I first started doing analysis, which is about 36 years ago. And so memory is more prevalent, memory is less expensive. So basically in the last release of Nastran 2012 and in the upcoming release of MSC Nastran 2013, we're better utilizing the memory available. And so we're basically reducing the amount of I/O time, which reduces the amount of wall time, and we're making more effective use of the CPU time. So on such a system, it's not unusual that in the past you saw large ratios between the wall time and the CPU time, and today utilizing your hardware, we're basically getting almost no difference between the wall time and the CPU time. So there are side benefits associated with that. It basically means that you need less disks, at least less disks for this portion of the system. Of course, you need, in general, more disks if you're going to be storing thousands of modes on very large models. Here's another example that's a customer problem. And again, by doing this type of model with a little bit over 1 million degrees of freedom, just comparing 2012.1 and 2012.2, we see almost a factor of 2.5 in terms of the wall time, so reduction of wall time, which is, as an engineer, that's very important. And of course, it really comes down to a massive reduction in the amount of I/O that was being used with MSC Nastran. So all of these things are important. There's a kind of, in terms of working with the software algorithms, we look at things from the large scale in terms of improving solver technology and eigenvalue technology. And we also look at things from the really low scale, what we call the math kernel scale. And so recently, work has been done in that area as well. The work is applicable whether or not you're using a single core machine, which is shown here, where we had a substantial reduction by this particular analysis in a SOL101 problem. It's about 8.4 million degrees of freedom. And we also see that in terms of parallel processing. We didn't even show the serial job because it was so much time. But effectively, what we're seeing with the newer releases of the product, effectively, that we're getting both improvements in scalar performance due to these kernel updates, and we're getting improvements or better utilization of shared memory processing when we have all the data effectively in nearby, so minimal amount of latency involved. Another area of utilization of the hardware better is we're always working with our partners, and this was one particular update we did working in conjunction with Intel. It's basically to use the AVX capabilities on the Sandy Bridge family of hardware, and so that effectively what we see is not just getting a new piece of hardware, but utilizing the new compiler settings to optimize the use of the hardware. We typically see somewhere in the area of 15% improvements in time and as much as 25% improvement of time. So working with our hardware partners is very important. So I'd like to introduce Dr. SoL101 from NVIDIA, who's going to talk to us about using NVIDIA hardware to improve the performance of MSC Nastran.
Thank you, Ted. Good morning, everyone. I'd like to start off by thanking our partner, MSC Software, for giving NVIDIA this opportunity to brief all of you on GPU computing with MSC Nastran. This is a joint development activity between MSC Software and NVIDIA. What I've got in this slide is a very brief description of how GPUs accelerate the computing. Now, for most of us as CAE users, the use of parallel applications that use multiple cores is a well-established technology. We are using that day in and day out, and Ted walked through a variety of use cases. However, what's emerging is the use of graphics processing units, GPUs, to accelerate the CPU computation. It's a heterogeneous computing model where the GPU serves as a co-processor to the CPU. By co-processing, a rigorous definition of that is a use of an accelerator. In this case, the accelerator is the GPU, to offload the CPU and to increase the computational efficiency. Now, we all know over the last couple of decades, CPUs have gone to great lengths to bridge the gap between processor and memory performance by introducing instruction and data caches, instruction-level parallelism, and a variety of such things. On the other hand, many core GPUs, these will often demand a high degree of fine-grained parallelism. GPUs use hardware multithreading to hide the latency of memory access. The key message that I'd like to leave you with on this slide is that the latency-optimized CPU cores are well suited for the logic and control parts of the workflow, while the throughput-optimized GPU cores are ideal for the data parallel and compute-intensive part of the workflow. So what you're looking at in this slide is how GPUs have shown to scale very well over time in both raw floating point performance, peak double precision floating point performance, and in terms of memory bandwidth. On the left-hand side, you're seeing the peak double precision floating point performance, how they're scaled versus the latest CPU architecture. Clearly, there is a gap. The gap between the latest GPU architecture, which is Kepler, and the latest CPU architecture, which is Sandy Bridge, there is about a 6 to 7x gap in performance. Looking at the right-hand side, that graph shows how the GPUs have scaled versus the CPU architectures measured by peak memory bandwidth. Once again, there is a gap of about 5x. Now, the simple reason for this lies in the architecture. The GPUs are populated with relatively simple processing cores compared to the CPU. There are more number of transistors that are available. Therefore, it's easier to pack more cores on the die in the case of a GPU than it is on a CPU. Now, why are these metrics important for MSC Nastran? If we were to consider a typical Nastran job, these are compute bound during the sparse solver phase, and other than the sparse matrix factorization, memory bandwidth and I/O performance are very critical. Ted talked to you about both memory and I/O performance. These are both very critical. So both of these, double precision floating point performance and memory bandwidth performance, are indeed significant for the use of MSC Nastran. The main point again here is there is a performance gap between the latest architecture of the CPU and the GPU, the CPU architecture being Sandy Bridge and the GPU architecture being Kepler, and that performance gap continues to widen. Now, what I'm showing here is the cost of a typical stress analysis static CAE simulation. We're looking at the cost of the equation solver and the simulation. In the table that you're looking at in the slide, there are two models. Both come from the powertrain industry, engine block models. One of them, less than 1 million degrees of freedom, about 700,000 degrees of freedom. And the amount of time spent in the equation solver is roughly about 54% for that model size. Now, looking at a larger model, about 5 million degrees of freedom, that time, that fraction of time spent on the equation solver goes up from 50% to 85%. So clearly, we are spending anywhere between 50 and 80% of the total time in the linear equation solver. And the larger the problem, the more time we spend on the equation solver. Now, this really makes the equation solution an obvious focal point for GPU acceleration. Now, here what I've got is the status of what you're going to see when MSC Nastran comes out. MSC Nastran 2013 comes out pretty soon, middle of the year. The Nastran direct equation solver is GPU accelerated. Nastran has got two direct solvers referred to as MSCLDL, which is the symmetric, and the MSCLU, the unsymmetric part, and both of these are GPU accelerated. The unique thing about this implementation supports all data types: real, complex, symmetric, and unsymmetric cases of the sparse matrix factorization. Now, I stress again here, the MSC Nastran implementation on GPUs is very unique. For one, it handles very large fronts during the sparse matrix factorization. It's the lowest granularity GPU implementation of a sparse direct solver that can handle very large sparse matrix sizes and is not constrained by the GPU device memory. And in terms of usage, any blocky or any fat BLAST3 code path is a potential candidate for GPU execution with MSC Nastran. The sparse direct solver impacts several solution sequences in MSC Nastran. Solution 101, the stress analysis, and solution 108, the direct frequency response analysis, see the most impact. In other words, they have the most potential for a high speed up with GPU acceleration, followed by some of the other solution sequences like solution 103, which is a normal modes analysis, or a solution 111, which is a modal frequency response analysis, or a solution 200, the design optimization solution, etc. Now, the implementation in MSC Nastran supports multiple GPUs, and it's supported both on Linux and Windows. Multiple GPUs can be used with a single analysis with the DMP option. Ted talked to you about the distributed memory parallel, the DMP option. Multiple fronts are factorized concurrently on multiple GPUs in this particular case. The NVIDIA GPUs that are supported as part of the GPU acceleration in MSC Nastran includes the latest architecture, which is the Kepler architecture. The GPUs are referred to as K20 and K20X. And with MSC Nastran 2013, it will be backward compatible, meaning it will support the Fermi architecture GPUs, which are the M2090 and C2075 GPUs, And we also support our Quadro class of GPUs, Quadro 6000 in particular, which is a combination of both visualization and compute in a GPU. The implementation in MSC Nastran is, as I said, very unique. And along that lines, the implementation is very easy to use and it's user transparent. If you look at the schematic that is shown at the bottom of that slide, 4 steps are involved in it. Step 1, the Nastran job gets launched on the CPU. Then Nastran automatically transfers the solver operations across the PCI Express bus from the CPU to the GPU. The number crunching, the compute-intensive part of the solution gets done on the GPU. And step number 3, GPU sends the results back to the CPU. And the Nastran job ends on the CPU. So really, the thing to emphasize here is the implementation is very user-transparent and easy to use. Along the lines, I took the liberty of putting out a couple of command lines here just to show you how easy it is to use GPUs with Nastran. The first case is an SMP. Ted detailed you on this, a shared memory parallel combined with GPU. Shared memory parallelism is a medium-grain parallelism, corresponds to loop-level parallelism. And DMP is a large grain and more at an algorithmic level like domain decomposition. GPU acceleration is supported with both the SMP option as well as the DMP option. Single GPU support with SMP and multiple GPU support with DMP. And the only thing that I'd like to highlight in the command line is what I've shown there in green, the GPU ID. In the case of SMP, you see GPU ID equals 0, which is really the only new parameter, the additional parameter that is needed to invoke the GPU option with the SMP capability. And now coming down to the next command, the DMP option, GPU ID equals 0:1, that refers to 2 GPUs, GPU ID 0 and GPU ID 1. And really, it's as simple as inputting those parameters in the command line, and then the GPU acceleration is automatically invoked by Nastran. I'm going to quickly run through a couple of examples here. What you're looking at in this slide is an example of solution 101 as well as solution 103. 101 is the standard stress analysis, and 103 is the normal modes analysis. And the left side of the chart shows 3 lines. The blue line is a serial run on a single CPU core. The red line is a SMP job with 4 CPU cores. And then the green line is a single GPU acceleration of this 4-core run. And looking at the speed up, you get an attractive speed up of about 6x over a serial run and more than a 2x over a 4-core run. Now, the other set of lines corresponds to solution 103. And there, if you look at the speed up from a single GPU acceleration, it's not as much as what you see with the solution 101 analysis. Now, the reason for this is, if you're looking at a modal analysis like a Lanczos solver, there are multiple compute-intensive pieces as part of this Lanczos algorithm. And the sparse matrix factorization that is performed on the GPU is one of the 3 main parts that are compute-intensive. Outside of the sparse matrix factorization, there is iteration on a block of vectors, Lanczos vectors, that involves a solve. And then these vectors needs to be orthogonal, so a Gram-Schmidt orthogonalization of the vectors. 3 compute-intensive parts. Only one of those parts run on the GPU, which is the sparse matrix factorization. So a reduced speedup in the case of solution 103 using the same piece of algorithm, the same sparse matrix factorization compared to a stress analysis. The next example is a real auto customer in Europe that is currently using GPU clusters for their NV8 simulation. And in this particular case, the solution sequence is solution 108. It's a direct frequency response solution sequence. And here you're looking at a car model with a cavity and with the internal cavity. And the typical responses as part of the NV8 simulation that are being computed here are the sound pressures at the ear locations of the driver and the passenger. And in the chart, what you're seeing is the performance scaling. You see the serial runtime And then the single GPU acceleration of a serial run is about a 5x in terms of speed up. And then you're seeing the SMP runs in the third and the fourth lines. And there again, the speed up is attractive with a single GPU accelerating the 4-core run by about 2x. Now, the real thing that I'd like to emphasize is what you see in the last two lines. An 8-core run with the DNP option, DNP equals 2, you've got 2 MPI threads. Each MPI thread spans 4 processes, total of 8 cores. And that job is getting accelerated by 2 GPUs by 2x. So 8 cores of Sandy Bridge performance is accelerated by 2 cores by 2x using 2 GPUs. A significant improvement as far as the solution time. Now, we also did a cost analysis on this particular model, the Solution 108, since this is a real customer model, Solution 108, and the customer is actually using GPUs, right, GPU clusters right now as part of their production capability. And here in this, you're seeing the same performances that I talked about in the earlier slide. A single core serial run, 4 cores, 4 core plus a single GPU acceleration, 8 cores, and 8 cores plus 2 GPUs. The blue lines and the green lines correspond to the performance scaling, and the red lines correspond to the solution cost. The solution cost itself, I've listed on the right-hand side how the cost basis is computed. It includes both the software cost and the hardware cost. The software licensing includes the SMP license, the exterior acoustics package, and the implicit HPC package that's required for the DNP runs. And it also includes the GPU licensing. One thing that I'd like to highlight here, MSC Software has put in a very attractive licensing scheme for the GPUs. And then I've also included the hardware cost in terms of the hardware node and 2 GPUs, each roughly costing about $2K. The thing that I'd like to highlight, the third set of lines, a single GPU acceleration of an SMP run, you get a 5x acceleration at a minimal increase in cost. That cost increase is just a 10% cost increase coming in from the GPU software licensing and the GPU hardware cost. And now if you look at the last line, an extra 13% increase in cost over the 8-core run yields 200% improvement in performance, going from 5.5x scaling to 11.1x, a 2x or a 200% improvement in performance over an 8-core Sandy Bridge run at a very minimal increase in cost. So really, this is a very attractive solution for realistic NVH type solutions. Now, the models that we talked about are all pretty much solid models. And in this particular case, this is a US auto customer. And in this case, the model is slightly different or quite different. If you look at the discretization of that model, it's majority shell elements, 2D elements like plates and shells, about 1 million shell elements compared to solids, which are about 10% of that. And here again, it's the NVH trimmed car body NVH analysis. And in the chart here, you're looking at a serial run, 4-core plus single GPU. And the thing that we're showing here is scaling across multiple nodes of a cluster. We go up to 3 nodes, and in each node, we are adding a single GPU. So a total of 3 GPUs across 3 nodes. And again, the scaling is very attractive. This is a shell model, and you still get about a 1.8x scaling going from a 4-core run to a 4-core plus single GPU acceleration. Now, the thing to emphasize here, this was asked in the earlier conference call this morning. In terms of model selection for GPU acceleration, fundamental to GPU computing is having enough work for the GPU. Solid models tend to create blocky fronts that are very attractive as far as the solver work in terms of computation. And it provides dense fronts and lots of computing for the GPU. But then you look at shell models, the combination of shells and solids, not necessarily that these are not going to be GPU accelerated. You still see a good scaling on these. What I'd like to emphasize here is blocky models, solid models generate large front sizes for the sparse matrix decomposition. Shells and plates tend to generate more sparsity compared to the solids. Computational work is extremely important as far as GPU acceleration. The next model is a powertrain model, and here this came from my colleagues at MSC Software in Japan. They work with a customer, a large auto customer in Japan. And here again is a realistic customer model. The thing that I'd like to highlight here is it's solution 111, unlike solution 108. 111 is a modal frequency response compared to a 108 direct frequency response. Direct frequency response is very attractive for sparse matrix factorization. Solution 111 has got other compute-intensive parts beyond the sparse matrix factorization. So here, if you look at the speed up, a single GPU acceleration of a single core is roughly about 1.7x, not as much as the 5x that we saw with the solution 108. If you just look at the sparse decomposition, the speed up is roughly about 3x. So Amdahl's law cuts it down to about 1.7x in terms of end-to-end wall times. Key message, a variety of solution sequences use the sparse solver. Some of the ones like 101 and 108, which exploits the sparse matrix factorization to a significant extent, are more impacted by GPU acceleration, more favorably impacted by GPU acceleration compared to the modal solutions. Now, some of the recommended configurations, I've got here a couple of configurations, server cluster as well as the workstation user. Doesn't matter what CPU that is, Intel, AMD CPUs, the latest architecture, Sandy Bridge architecture, doesn't matter, Westmere, Sandy Bridge. Key thing is, we recommend the Tesla Kepler GPUs, K20, K20X. The older architecture Fermi GPUs also work very well. M2090 GPUs, these are the GPUs recommended on the server side. Memory is extremely important. Configure each node with at least 128 gigabytes of memory. As my colleague Ted pointed out, memory these days is very cheap, so it's not a pricey item. It's good to configure with sufficient memory so I/O is minimized. And on the workstation side, smaller models, single GPU acceleration, and again, memory is important, about 96 gigabytes of memory. My last slide there, we've got a significant amount of tools and resources on GPU computing with MSC Nastran. MSC recently did a partner showcase highlighting the NVIDIA GPU capability, and there's the link there, quick reference guide that's got details about the system cell parameters. And if you've got questions, please feel free to contact either myself or Dr. Ted Wertheimer. Our email addresses are listed there, and we'll be glad to share more details with you. Thank you very much. Passing it back to Ted.
Thank you. So we're going to continue on with talking about a few other applications and how we use high-performance computing to improve your ability to solve problems. This was some work that we did between the 2011 release and the 2012 release, where we basically improved the capability to do performance for frequency response simulations. It's important to acoustics, typically getting 3 times faster performance than we did in previous releases. Another 2 other things that we did in the area of acoustics, MSC was well known for doing fully coupled interior and exterior acoustics. That's a very accurate procedure to do, but sometimes it's not quite necessary. So we also added a weakly coupled acoustic technique, and for many problems, this can be 3 to 4 times faster for the simulation. Another area is calculation of the participation factors. The participation factor is an extremely parallelizable event. So basically what we did was we continued to make performance on the eigenvalue abstraction portion. We continued to make progress in the frequency response portion, but we also did substantial progress in this panel participation. So altogether, it's not just attacking one part of the problem, but it's attacking all parts of the problem to get improved performance. Optimization is also an area where you can make great benefits in high-performance computing. When we go to larger models, not only are we going to larger models from a degrees of freedom perspective, but often we're also going to much larger models in terms of the number of design variables. We're going to these higher number of design variables because, again, we often want to minimize the thickness, minimize the weight of our structure to get a more efficient design in the analysis. So one of the things we've also done is improve some of the core algorithms in the optimization module. And these numbers are very impressive in terms of what we have achieved over the last few years in terms of improving the algorithms. Finally, I also want to show a couple of engineering models that have been performed recently in terms of giving the idea of the problems that people are doing and the solutions they're obtaining. So this was basically a full automotive, or actually with the body and white part of the automotive, but basically 12 million degrees of freedom, 418,000 design variables, looking at optimizing the system both in terms of the frequency content of the system and doing that analysis over 10,000 modes. So this was basically, we've replaced the kernels of our system going from big dot to IP-op, which basically improved not only the performance of the system, but gave us better results. We got more smoother results in terms of what the thickness distribution should be. And so that allows you to take that information and utilize it in your designs in terms of getting a manufacturable type solution. Also want to quickly talk about aeroelasticity. Aeroelasticity is also an area where we've done performance improvements. Aeroelasticity, what we're really talking about is doing flutter analysis. Of course, it's very important for all planes. It's becoming even more critical when you're talking about planes that are lighter weight, such as composite design, and longer wingspan, which means more flexible wings. So effectively, again, looking at some comparisons in recent technology gains in terms of high-performance computing, reduction in computational time, and this is associated with the splining option, reduction of the I/O time associated with it, and reduction of the amount of disk space required in the analysis. So I'm now going to pass things along to my colleague to talk a little bit about explicit dynamics with SOL101.
Hi folks, this is Casey Hidari. On behalf of MSC Software, I would like to welcome you to our webcast related to HPC. Let me introduce you to Solution 700 and say a couple of words there. As you know, Nastran is well known for dynamics and linear analysis, but we do have a very powerful explicit nonlinear solver under Nastran, which is based on two different solvers. One is based on LS-Dyno and for the structural solutions, and the other is based on the Dytran for fluids and fluid structure interaction. Both of these solvers are fully integrated inside Nastran, and they work in the Nastran modeling environment. The DMP implementation in SOL100 is a fully coupled solution. It supports DMP for structures, for fluids, as well as FSI applications. The DMP implementation for the fluid solver and the coupling is based on the Dytran DMP technology, Dytran being a product that we have and is the predecessor to Solution 700 in Nastran, and it uses MPI and has fully parallelized the Eulerian solver, the finite volume solver. The way it works is that it's very similar to the domain decomposition, where we take the Eulerian domain and partition it into subdomains or a smaller cubes, if you will, and those cubes are then spawned over the distributed processors across the network. The DMP for structures and contact is based on the LS-Dyno MPP version. And again, here also the structure is subdivided into a smaller domains, and these domains are residing over the number of the processors. So both the structure and the fluid domains are both broken into different parts, and these domains are basically distributed. This is a chart, some of the progress that we've made since 2010. It shows the performance and the speed up factors in 2010. This is a chart at the top left. We have run numerous benchmarks to gauge the performance and scalability. I think that we run at least 23 mid-size and large FSI models that were tested with varying features like with coupling and without coupling, like polar and fluid only, single material, multi-material, benchmarks for different applications with different industries like airbags, explosions, impact, crash, what have you. So these are the representative charts. Each color shows you a different benchmark problem. The size of these models were as large as 2.2 million elements, and the jobs were run on a Linux server with Red Hat 5.4 with Intel Xeon processor, and we ran up to 32 cores. The chart on the top left shows the elapsed time and scalability as the number of the cores are increased from single core to 32 cores. The chart to its immediate right on the top shows the speed up factors. So, for example, if you run a job on 32 cores, you can get 17 times a speed up factor compared to a serial run. Since 2010, we have made a lot of improvements to our DMP FSI algorithms by removing the bottlenecks in coupling and clumping routines, clumping being where there are different materials interact inside one element. Making the MPI calls more efficient and basically trying to reduce the overhead costs smaller and the I/O costs smaller. These updates that we've done since 2010 has resulted in dramatic performance improvements as shown in 2013 chart right below. We run the same jobs with version 2013 of Nastran, which is coming out pretty soon, on the same machine, and we were able to reduce the CPU time significantly across the board. Looking at the elapsed times, for example, some jobs that took about 23,500 seconds on a single core in 2010, with the version of 2013, it took only about 7,800 seconds, almost 1/3 of the time. We were also able to improve the speed up factors from 17x to 28x with 32 cores in 2013. This is a cleaner chart which shows you basically the performance of MSC Nastran 2013 and shows the speed up factors. Again, we had very good performance improvements for large models and complex CPU-intensive applications like hydroplaning, glass, flushing, and other large FSI applications. Overall, the performance improvements for Nastran 2013 were up to 63% on single core and up to 133% on 64 cores compared to the previous version 2012.2. There will be a paper published with the results of the 64 core in our upcoming users conference on May 7 and 8 in beautiful Orange County. So I urge everybody to come and attend that users conference. The speed up factors for 1 core versus 64 cores were up to 35x. This is the chart which shows you basically different applications across the major industries that you can use Solution 700. Automotive, aero, defense, and consumer. In automotive, you have the crash, you have the tire performance, fuel tanks, fuel pumps. In the aerospace, you have the bird strike and crash worthiness. In defense, blast and explosive is a very common and popular application. So what I'd like to do is to show you a couple of examples in these industries so that you can use the DMP capability for SOL700. This is a three-car crash model. This model is about 800,000 nodes and 780,000 elements. We run this job on SGI IS8400 machine, and we ran it up to 512 cores. As you can see, we got excellent scalability going from a serial processor to 512 cores, and you can get 77 times performance improvement running it on 512 cores. The next application is in tire industry. Tire hydroplaning is a very complex FSI application. Tire itself is highly nonlinear. It's made of rubber and it's reinforced with a steel belt. It has composite behavior. It has many layers, and it is inflated and it carries the weight of the vehicle. Now you take this complicated structure and then you roll it over on a wet surface or snow or mud to basically predict the tire footprint. Very complex. A few years ago, an application like this would take about 3 weeks on a very fast computer. But now, with the use of DMP and parallel processing, you can basically reduce the simulation to only a few hours. This is a benchmark that was given to us by one of our customers. This is a very complicated tire model, came from Hankook Tire in Korea. There are about 2 million elements in this model, and the customer run this job with 2012 version of Nastran and compared that with the previous version of 2012. And they were able to get more than 300% performance improvement on a number of cores, which I'm not allowed to disclose. With version 2013, we're expecting even better performance. Another application was from defense industry. This is a landmine blast application. The model had 2.8 million Eulerian elements and 660,000 structural elements. And the customer ran this job up to 4 processors. And on the serial processor, they were able to get 31 hours to complete the job. As they increased the number of the cores to 2, they were able to basically half the CPU time, and going from 2 cores to 4 cores, they were able to complete the simulation by 11 hours, almost 1/3 of the time. So with that, I would like to conclude my presentation and return back the control